Everyone knows the next decade of energy transition faces massive hurdles. But here is the truth most headlines miss. It will not be slowed by technology itself. The real bottleneck is grid infrastructure. We are underestimating how big of a choke point this physical limitation creates for artificial intelligence growth. By the end of this explanation, you will understand why the future of AI depends less on better algorithms and more on copper wires, steel towers, and bureaucratic permitting timelines that simply cannot move fast enough to keep up with demand. For years, the narrative around artificial intelligence has been entirely about software capability. We have obsessively tracked model architectures, chip manufacturing speeds, and parameter counts as if those were the only variables in play. The assumption was always that once we built a smarter system, power would simply be there when needed. That view is now dangerously obsolete. The physical constraint has shifted from generation capacity to something far more rigid: grid-supporting equipment supply chains. This includes transformers, high-voltage inverters, and the copper required to connect them all. Consider the data projections for 2030. A study by Johns Hopkins University projects that shortages in this grid-supporting equipment will leave a massive gap of roughly 270 gigavolt amperes. That is not a minor shortfall. It represents a deficit where demand vastly outstrips what can physically be delivered. The primary binding constraint here is copper, the backbone of any electrical transmission system. Because global manufacturing cannot scale fast enough to meet this surge in demand, we are facing a hard stop on expansion, regardless of how mature our renewable technologies become. The mismatch between software speed and physical reality has never been more stark. Data center electricity consumption is projected to more than double from 415 terawatt-hours today to 945 by 2030. This demand comes from training massive models and running inference for billions of users simultaneously. Yet, the infrastructure required to deliver this power faces a 3 to 5 year lag in permitting and installing high-voltage transmission lines. You cannot build an AI cluster faster than you can get it connected to the grid. The result is a temporal mismatch where compute clusters will be ready before the physical pathways exist to fuel them. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates a scenario where adding generation capacity yields diminishing returns if the interconnection points are not there first. Look at South Korea as a concrete example of this failure mode. In that nation, renewable capacity increased sixfold over recent years, yet actual power generation only tripled. The extra wind and solar farms sat idle because they could not connect to the transmission network fast enough. This proves that adding green energy without building the lines to move it is an exercise in futility. The bottleneck has moved upstream from where we generate electricity to how we route it. Now consider why this matters for artificial intelligence specifically. We often think of AI growth as a software problem, but it is fundamentally becoming a physical logistics challenge. The limiting factor is no longer model architecture or chip manufacturing speed. It is the bureaucratic and lead times required to route power from remote renewable sites to urban data center hubs where these systems live. Every time we try to expand an AI capability, we hit this wall of permitting delays that takes years to clear. Some might argue that co-optimizing renewable sizing with storage could solve this. We can reduce the need for new transmission lines by about 10% through strategic siting and placing batteries next to generation sources. This mitigation is valuable because it lowers the strain on specific corridors. However, we must be honest about its limits. A 10% reduction cannot overcome a deficit that threatens nearly 30% of our equipment supply chain in 2030. While grid-enhancing technologies offer some breathing room, they do not eliminate the fundamental delay in siting and permitting high-voltage interconnection lines. The critical knowledge gap lies in how we quantify the scaling timeline for copper and steel production versus accelerating AI demand. Current decarbonization models frequently assume that grid-supporting equipment will be available when needed. They often overlook the manufacturing feasibility required to meet this surge. This assumption significantly underestimates the physical reality of what is actually possible within a decade. We are building our energy transition plans on paper assumptions rather than hard material constraints. This shifts the entire conversation from whether AI can work to where that power will come from and when it will arrive. The grid has become the new hard limit on scalability. If we cannot move copper fast enough, no amount of software optimization matters. We are seeing a redefinition of what success looks like in this sector. It is not about who builds the smartest model first, it is about which companies can secure the physical infrastructure to run them reliably for decades. The implication for investors and engineers is profound. You cannot optimize your way out of a supply chain crisis or a permitting backlog. The critical path now involves navigating complex regulatory environments, securing long lead equipment like transformers that have years-long delivery windows, and ensuring copper production scales in lockstep with demand. This is the new engineering frontier, not writing code, but building the physical arteries that will carry the lifeblood of the digital economy. We are entering a decade where the most valuable asset might not be an algorithm or a dataset. It could simply be access to reliable power delivered through a grid that finally has enough copper and steel to handle it all. The gap between what we want AI to do and what our infrastructure can support is widening, and closing it requires a level of physical construction effort that society may have underestimated until now. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.